Okay, in problem 5, we start out with this particle here at point 1, and we're given its initial speed. It goes in the negative x direction, right? And it's only allowed to travel along this x-axis. It has a mass of 1.10 kilograms, so let's just say mass equals 1.10 kilograms. Okay, and it's traveling initially this way. And so we want to find out, for the first problem, we want to find out if it can reach 1.0 and what's its speed there. Okay, so right here is 1.0. And so spot 2, we want to find out if it can reach spot 2. So, again, as with so many of these things, we do energy balance. So, kinetic energy here, potential energy here, equals, and then mechanical energy here. So let's just start by calculating these. So mechanical energy at the beginning is going to be 1/2 mv squared. And I'm actually going to go ahead and calculate this. So 0.5 times 1.10, so 1/2 times m times 6.5 squared. And that gives us 23.2, I'll say 23.24 joules. Okay, so equals 23.24 joules. Okay. Potential energy at this point, well, this you just read off the plot. It's right here between 4 and 5 meters, which means it's at this 25 joule potential energy mark. So they haven't told us where this potential energy is coming from. And that's not really relevant to the problem. We just are told here's what it is at these different points. And so the point is it doesn't really matter what this potential energy is from, whether it's gravity or some kind of weird electromagnetic force or whatever. They're just telling us what it is by position and telling us to use that to determine where this thing goes. So potential energy is quite simply, read it off the plot, 25 joules. Now, mechanical energy, total mechanical energy, is the sum of these two. So it's 48.25 and 23 is 48.24 joules. Okay, so we're all good so far. Now at point 2, it's going to have a kinetic energy, it's going to have a potential energy, and it's going to have a mechanical energy. I believe it said no non-conservative forces are involved. Yeah. So all that acts as this conservative force, or whatever conservative forces contribute to this U. So what this means is, as it cruises to the left, we're trying to find out if it can get to this spot. It needs to have more potential energy here to be here than it needs to have here. So the potential energy required is increased. You can think of this as being like going up a hill. So right here, it's got a certain speed and it's a certain height, and we're asking, is it rolling fast enough? So it's just rolling this way, not being powered or pushed or anything. It's just rolling this way with its own momentum and its kinetic energy. And we want to know, is it going fast enough that it can roll all the way up this hill? And if so, what will be its speed at the very top? So, this is just a case where mechanical energy is conserved. So we actually have the same mechanical energy at 2 as we have at 1. So 48.24 joules. Okay. Potential energy here is going to be 40 joules. It has to have 40 joules of potential energy here. It only had 25 back here, so it's got 40 joules here. And mechanical energy, as you recall, is the sum of kinetic and potential. So since we know what the potential energy is, we know what the mechanical energy is, we can just subtract these two, right, to find out that kinetic energy at this point is 8.24 joules. And they want to know how fast it's going. So that's going to equal 1/2 m. I'm going to subscript these things. Velocity 1 at point 1, so this is going to be velocity 2, and this I'm going to put 1 there, so because I want to put an mv2 squared here. So this tells us then v2 equals square root of 2 ek over m. This is just a way to invert it and find v2's, given that we already have this. So ek divided by m, so it's 8.24. Let's see, 2 times 8. I want square root. Square root of 2 times 8.24 divided by 1.10 is going to give us 3.87 meters per second. So Actually, what this tells us is equals plus or minus. So V2 equals plus or minus, I already forgot what it was, 3.87 meters per second. 3.87 meters per second. The fact that we don't know what direction it's going doesn't actually bother us, because all they ask us for is its speed. So 3.87, and then they want to know what speed there is, meters per second. So let's go ahead and submit that. And boom, got it right. Okay, so what are the magnitude and direction of the force on the particle as it begins to move to the left of x equals 4 meters? So as it's starting here, it's going left. What's the force that's resisting it here? Well, so one way to look at it, the force is whatever is causing this potential energy. So the force is the force that derives this potential energy, you might say. So what's the work required? How much work do you have to do to go up the hill? Or how much work does this force do on you as you go up the hill? That's just the change in potential energy, right? So the work going up the hill, so the work going from point 1 to point 2 is negative 15 joules. That's the work this force does on you. So your kinetic energy goes from 23 at the bottom of the hill to about 8 at the top. That means this force did minus 15 joules of work on you, and that's reflected in the fact that its potential energy increased. Okay, so the distance over which that work is done is, the displacement over which that work is done, it goes from 4 meters to 2 meters while this work is being done on the slope, right? So negative 2 meters. So what we have here is a case where, remember, work is force dotted with displacement. And our displacement here is negative 2, or it's 2 meters in the negative x direction. Our force is going in the positive x direction. So we can really just do scalars here, because this is all in line with each other. It's all happening along one line. So we can do negative 15 joules equals F times negative 2 meters. And so what this tells us then is that F equals, we can cancel out the negative signs, 15 joules over 2 meters, which is going to be 7.5 is 15 divided by 2, and then a joule, you'll recall, is a Newton meter, so, and it's divided by a meter, so 7.5 newtons if we cancel the meters out. So that gives us the correct unit. So what they're telling us is that the force due to this potential on the object as it's moving up here is 7.5 newtons in the positive x direction. So 7.5 newtons in the positive direction. Okay, so let's go to 5 and boom. Okay, now part 2, suppose instead it went the other way and has to climb this bigger hill, and so does it reach 7.0 meters? So here's part 3, or stage 3, sorry. Okay, sorry, state 3. State 3, there we go. At 3, well, you can probably already guess this, but kinetic energy, potential energy, and mechanical energy. So mechanical energy is still going to be the same. It's this initial state here, and we had V1 squared. So we're changing the sign of V1, but then when you square it, it becomes the same. So total mechanical energy is 48.24 joules. And potential energy at this point is 60 joules, which means you have about negative, what does that be, 12? So negative 11.76 joules of kinetic energy. Well, that doesn't work. You can't have negative kinetic energy, because then you'd have to have an imaginary velocity, right? Kinetic energy is 1/2 mv squared. Mass is going to be positive, 1/2 is positive. So for this to be negative, you'd have to have an imaginary number for velocity. So that does not work. That means it does not get up to point 3. How far up does it get? Well, it gets to the point, so there's some point, I'm going to call this 3A here. And in fact, I'm going to erase 3 because it's just taking up space that I need. So let's cut that. There we go. Okay. And eraser. Get rid of the rest. Okay. So at point 3A, we have kinetic energy equal to 0, and potential energy equal to something, and mechanical energy, well, the mechanical energy is going to be 48.24 joules, which means the potential energy has to be 48.24 joules. So on this plot, I mean, this is not to scale, unfortunately. This is kind of a shitty plot, but this level here is where potential energy is 48.24 joules. Sorry, pardon the chicken scratch here, but right here is where U is 48.24 joules. To find out where that is between this 5 and 6, we literally just have to do a proportion. So this goes back to, like, I mean, God knows how old you were when you first learned this, but here it comes. We've got this slope here. Actually, it's more like a line like this. The coordinates of this are 5. So at 5 meters, we're at 25 joules. 25 joules. And the coordinates at this end are 660. And then right here is a spot where it is x comma 48.24. And so quite literally, get ready to be annoyed, we have to do, let's see, so we have to do, let me close my parentheses here to be sort of, neat. Sort of neat. That's the best I can do, is sort of neat. Okay, so we have to do 6 minus 5 over 60 minus 25 equals x minus 5 over 48.24 minus 25. Barf, barf, barf. Okay? So, what this gives us is then that, let's scroll this down a little, x minus 5 equals, 6 minus 5 is 1, and this here is 60 minus 25 is 35 times 48.25 minus 25, so 23.24. Okay, so x is going to equal 23.24. Why am I looking at this? So 23.24 divided by 35 plus 5. X is going to equal 5.664. X equals 5.664 meters. So 5.664 meters, and let's see if I got that right. Okay, got it right. Magnitude and direction of the force in the particle begins to move to the right of x. Well, that's not terribly hard. This is the slope here, actually, right? This is that hill that we had to go up, and we use the same logic there. So we say work equals force times displacement, and so the force we want to find is the work. As you go up this hill, you lose. If you went all the way up this hill, you would lose 35 joules, and that's going to equal force times the 1 meter you traveled. So the force is going to equal negative 35, and divided by 1. Divide joules by meters, you get newtons. So our force should be negative 35 newtons. 35 newtons in the negative direction. Let's hope I got this right. 35 negative, and almost out of time, so hopefully this is correct. And hooray, I got it. Okay, problem 6 coming up.